So, in the last lecture what we have done, that is finite Fourier transform. Although we have done the Laplace transform and Fourier transform, but for solving boundary value problems, it has been observed that the variables or the parameters which we are using, that may not lie in 0 to infinity or minus infinity to infinity, but they may have a finite range, say 0 to L, 0 to 4, something like this. So, in that case directly we cannot use the Fourier transform or Laplace transform. For that reason, the finite Fourier transform has been developed. In the last lecture we have discussed what is the finite Fourier transform and what are the properties of the finite Fourier transform, along with the how to find out Fourier sine transform of del f del x, Fourier sine transform of del 2 f del x square, or the finite cosine transform of del f del x or finite cosine transform of del 2 f del x square. In this lecture what we are going to do, first we will solve few problems, then we will take some finite boundary value problems and using the finite transform how to find out the solution of those finite boundary value problems. So, let us take the first example. We want to find out the Fourier sine and cosine transform of f x equals x square, where x lies between 0 to 4. So, here you see, in general if I have to use the Fourier cosine and sine transform, x should lies in between 0 to infinity, but here the function is defined 0 to 4. So, we are forced to use the finite Fourier cosine or sine transform. So, we want to find out the first Fourier sine and then Fourier cosine transform of this function. Therefore, your f x is given as x square in where 0 less than x less than 4, it is given to us. So, finite Fourier sine transform of f x, please note that although the similar notation we are using, but this is finite Fourier transform of f x. This is equals to, from the definition, if it is from 0 to L, you know it, 0 to L f x into sin n pi x by L into dx, from the definition whatever we have seen earlier. Here f x is x square and your L is 2 here, sorry, L is here 4. So, f x is x square and your L is 4, since the function is defined from 0 to 4. So, that the integral you can write down 0 to 4 x square sin n pi x by 4 into dx. And if you evaluate the integral, I am not telling that how using integration by parts you can evaluate the integral, since we have done all these things earlier, the evaluation of integrals. So, the result I am directly writing as this is equals minus 64 by n pi into cos of n pi plus 128 by n cube into pi cube into cos of n pi minus 1. This will be the result. So, therefore, finite Fourier sine transform of f x, from the definition we know it 0 to L f x sin n pi x by L dx, and for this case your function is x square and x is defined from 0 to 4. So, that your L is equals to 4. So, if I put it, the integral becomes 0 to 4 x square sin n pi x by 4 into dx, and you will get this particular result. So, just let us see once. So, once I am doing this finite Fourier sine transform, I am writing 0 to L f x sin n pi x by L dx, and where your L lies between 0 to 4 and f x is x square. So, if I evaluate the integral, I will obtain this particular result. Now, on the same way I can find out the Fourier cosine transform also. Let us see it. Finite Fourier cosine transform of f x. So, f c of f x, finite Fourier cosine transform of f x is equal to 0 to L, from definition it is f x into cos of n pi x by L into dx. So, in the case of Fourier sine transform, it is 0 to L f x sin n pi x by L dx, where x lies between 0 to L, whereas for the case of Fourier cosine transform, it is 0 to L f x into cos n pi x by L dx. So, that this equals, you can write down, your L is 4. So, 0 to 4 f x is x square into cos of n pi x by 4 into dx. And if I evaluate the integral, I will obtain the value as 128 by n square pi square into cos of n pi. So, cos of n pi value you can put it here. So, your Fourier cosine transform of f x, where f x is x square and x square lies between 0 to 4, is equals to 128 by n square pi square into cos of n pi. So, if you just see it once, we have done it up to this. So, Fourier cosine transform of f x is this one, and this is equals to 0 to 4 x square cos n pi x by 4, and this equals 128 n square pi square, 128 by n square pi square into cos of n pi. So, like this way we can find out the Fourier cosine, finite Fourier cosine transform or finite Fourier sine transform of a function whenever the function is defined in a particular range, say from x from 0 to L. Now, we will not go for more examples, directly we are going to the solution of boundary value problems using finite Fourier transform. So, we will go for this thing. The first problem here is, please note one thing, for the solution of boundary value problem using finite Fourier sine or cosine transform, which one I have to choose, it depends on certain criteria. So, we are saying that choice of finite sine or cosine transform is required whenever, if for finite sine transform value of u0t and value of ult must be known to us, then only I can use Fourier sine transform. So, please note that for Fourier sine transform value of u0t and ult should be known, whereas for finite cosine transform value of ux0t and uxlt must be known, that is the first derivative of the function at x equals 0 and at x equals L with respect to x should be known. So, please note that whenever I want to solve a problem using finite Fourier sine transform, I need to know the value of u0t and ult, whereas for finite cosine transform I need to know the value of ux0t and uxlt, otherwise I cannot find out the solution. So, please remember these 2 points, that for finite Fourier sine transform u0t ult is required. Similarly, for finite cosine transform ux0t and uxlt is required. So, let us take a problem. I want to find out the Fourier sine transform of the function del u del t equals del 2 u del x square, where x lies between 0 to 4 and t greater than 0. It is given to me that u0t equals 0, u4t equals 0 and ux0 equals 2x, when x lies between 0 to 4 and t greater than 0. So, here if you see, firstly I cannot take the Fourier sine transform with respect to t, because range of t is from 0 to infinity. T varies from 0 to infinity, whereas x varies from 0 to 4. So, whenever I have to take it, I have to take it with respect to x. Now, the value of u0t is known to me, it is given. Value of ult, that is L is 4 here, u4t is known to me. Therefore, for this particular problem, I can use the Fourier sine transform with respect to x. So, please note that since u0t and u4t values are known to me and x lies between 0 to 4, therefore, I can use the Fourier sine transform with respect to x. Let us see the solution process. here. So, your problem just I am writing del u del t, this is equals to del 2 u del x square. So, your x lies between 0 to 4. So, what you will do, apply, I am just writing here, apply finite Fourier sine transform with respect to x, and this was possible since value of u 0 t and value of u l t is known to me. So, I am applying finite Fourier sine transform with respect to x on both sides of the given differential equation. So, from the definition, the left hand side will be 0 to 4, here L is 4, del u del t into sin n pi x by 4 into dx, whereas your right side will be 0 to 4 del 2 u del x square into your del 2 u del x square into sin n pi x by 4 into dx. Now, you see the integral on the left hand side. So, after taking the finite Fourier sine transform with respect to x on both sides of the given equation, from definition of finite Fourier sine transform, I can write down 0 to 4 del u del t sin n pi x by 4 dx, f x into sin n pi l by dx. So, L is 4. So, this equals 0 to 4 del 2 u del x square sin n pi x by 4 into dx. Now, I am making the finite Fourier sine transform with respect to x. So, del e t, this can go outside. Once I am taking this del t outside, therefore, it will become your basically it is, I can bring it outside d dt of 0 to 4 u sin n pi x by 4. I am writing d dt because on the left hand side it is independent of t, and this right hand side will be from the definitions n square, please see the definition, I am not explaining that again, into n square pi square by 16 into u bar h plus n pi by 4 into u 0 t minus u 40 into cos n pi. This already in the last lecture we have done it. For this reason, I am not explaining this part. This is standard one, 0 to 4 del square x del square u del x square sin n pi by n pi x by 4 dx will be minus n square pi square by L square, here L is 4. So, that minus n square pi square by 16 into u bar s. Please note that this u bar s is nothing but the Fourier finite Fourier sine transform of the function u x t plus n pi by L, L is 4 again. So, it is n pi by 4 into u 0 t minus u L t into cos n pi. So, L is 4. So, u 0 t minus u 40 into cos n pi. So, therefore, you are getting this thing. Now, the left hand side what will happen, 0 to 4 u sin n pi x by 4 dx. This is nothing but u bar x, that is finite Fourier sine transform of u. So, left hand side we can write down d u bar, basically s I am writing to denote that u bar s is the finite Fourier sine transform with respect to x into dt. This is equals a minus, the values are given as u 0 t is 0. This particular value is given from the condition as 0. u 40, this is also equals to 0 is given. u 40, this value is also equals to 0. So, once I put this thing, so the second term will vanish. So, that you will have only minus n square pi square by 16 into u bar s. So, please note that I had the given PD del u del t equals del 2 u del x square. Using the PD, I am just using applied finite Fourier sine transform with respect to x on the both side of the given equation, and I am converting it into an ODE of the form d u bar s dt equals minus n square pi square by 16 into this u bar s, and I can find out the solution of this thing. So, this is a simple ODE. So, directly I can write down the solution of the ODE as u bar s, this is equals to a into e power minus n square pi square t by 16. This I can write down the solution as, you can go through this, simply you can write down u bar s equals a e power minus n square pi square t by 16. Now, my next job is to find out the value of this constant a. Now, one more condition has been given to us, that is u x 0 equals 2x, where your x lies between 0 to 4. It is given to us. At t equals 0, what happens? At t equals 0, what is u bar s? It will be 0 to 4. From u bar, definition of u bar s, it is 0 to 4 u x t. At t equals 0, it will be u x 0 into sin n pi x by L, L is 4 into dx. So, that this your u x 0 is given as 2x. So, this equals, you can write down 0 to 4 2x into sin n pi x by 4 into dx. This equals, you can write down, if you evaluate the integral by parts, minus 2x into 4 by n pi, sin will be cos. So, this is n pi x by 4, and the other term will be 2 into 4 by n pi into 4 by n pi, and this will be sin n pi x by 4. So, if I evaluate the integral, I will obtain this, and the limiting value will be from 0 to 4. So, if you put the limit on this, you can see that the value will become 32 into minus cos n pi by n pi, and this is nothing but again 32 into, I can write it as minus 1 whole to the power n by n pi. So, that actually this will become minus 1 to the power n plus 1 into 32 by n pi. So, at t equals 0, you are obtaining u bar s as this. Also, at t equals 0, your u bar s from this term, at t equals 0, your u bar s is equals to a, because t is 0. So, this e power term will not be there. So, therefore, u bar s I am getting this, and at t equals 0 also u bar s is this one. So, using these two, I can write down that my a is equals to 32 into minus 1 to the power n plus 1 divided by n pi. So, that if I substitute the value, I will obtain u bar s equals minus 1 to the power n pi into e power minus n square pi square into t divided by 16. So, once I obtained u bar s in terms of t, now I can write down u x t. U x t from the definition, it is 2 by L, that is 2 by L is 4, summation n equals 1 to infinity u bar s into sin n pi x by L, that is 4. U bar s, please note that whenever I am taking the inverse finite Fourier sine transform, in that case your x t is becoming a summation about this. Why this summation is coming? This we explained in the last lecture. So, by the formula 2 by L summation n equals 1 to infinity u bar s into sin n pi x by 4. So, that this is equals to, you can write down, this is half will come in summation n equals 1 to infinity 32 into minus 1 to the power, sorry, this will be n plus 1. Please note this, u bar s will be 32 into minus 1 to the power n plus 1 by n pi into e power minus n square pi square t by 16 into your sin n pi x by 4 into sin n pi x divided by 4. So, this 32 you can simplify it, 16 by pi summation n equals 1 to infinity minus 1 to the power n plus 1 divided by n e power minus n square pi square t by 16 into sin of n pi x divided by 4. So, please note that once I am getting u x t, u bar s, from there u x t I can find out like this way, and ultimately the solution of the given partial differential equation becomes u x t equals 16 by pi into this result. So, let us see it. This was your actual example. So, what we have done? We have taken the finite Fourier sine transform with respect to x on both sides of the given partial differential equation, and as I told you at the beginning, since I know u 0 t, u 4 t, so I can use the finite Fourier sine transform. Once I am doing it, I will get 0 to 4 del u del t sin n pi x by 4 equals 0 to 4 del 2 u del x square sin n pi x by 4 dx. So, d u bar s dt, this will be equals to the left hand side. I have already explained why d dt of u bar s will come on the left hand side, and this del 2 u del x square sin n pi x by 4 dx is how much, that also evaluated earlier. So, we are just putting the value minus n square pi square by 16 u bar s plus n pi by 4 into u 0 t minus u 4 t into cos n phi, and we know u 0 t is 0 and u 4 t equals 0. So, if you substitute, the second term of the right hand side will vanish. So, you will have only this, and where u bar s is the finite Fourier sine transform of u. Once I am getting this, I can obtain u bar s equals some constant a into e to the power minus n square pi square t by 16. This is the solution of the ODE which I obtained over here, that is d u bar s dt equals minus n square pi square by 16 into u bar s. So, I have to find out the value of u bar s. I know u x 0 equals 2 x when x lies between 0 to 4. So, at t equals 0, your u bar s equals 0 to 4 u x 0, that is 2 x into sin n pi x by 4. If I evaluate the integral, I will obtain this value 32 into minus 1 to the power n plus 1 by n pi. So, that at t equals 0, your u bar s is this quantity, also u bar s equals a at t equals 0. Therefore, a will be equals to 32 into minus 1 to the power n plus 1 by n pi. So, u bar s I can obtain by using the value of a. So, using the inversion u x t will be equals to 2 by L summation n equals 1 to infinity u bar s into sin n pi x by 4, and we are substituting the value of u bar s in terms of t whatever I am obtaining. So, that after evaluation you will obtain this result. So, by this way I can find out the value of the u x t whenever the given partial differential equation along with the conditions. Let us take another example of some other form. Here I am telling using some finite transform, when del v del t equals k del 2 v del x square, x lies between 0 to pi, t greater than 0, with del v del x equals 0 whenever x equals 0 and x equals pi, t less than 0, and v equals f x when t equals 0, where x lies between 0 to pi. If you see the particular problem, so let us do one thing. Due to shortage of time, let us continue this problem in the next lecture because it will not be possible to finish it by next 3-4 minutes. Thank you.